Okay, just to note at the beginning that the slidey force, which is mg sine theta,
on a
does
ramp.
not cause torque. Since it's applied at the center of the object. But the friction force does cause torque because it's applied at the radius. Okay, so just to be aware, if you are rolling, then there is friction. If there's no friction, there's no bothering to roll, it just slides down. Sort of imagine what happens on ice. Okay, so there's two ways to actually do this. You can do part B first, using energy to solve for V, and then use kinematics to solve for A. I'm going to show you A first, and then we'll talk about the other way around. So okay, so what is the friction force? In order to get the friction force without looking at energy first, well, let's balance torques. It's a hollow hoop, so we've got mr squared. I'm going to turn alpha into A over R. Friction force is acting at a distance of R. So notice if you start canceling R's, let's just cancel some in blue. Bing, bong, bing, bong. Oh, the friction force is ma. So that doubles ma. Yeah, canceling capital M. There's only one mass. And divide by 2. Okay. Then to derive the expression for the speed, we can use kinematics. The distance is L, the length that we're traveling. It's not H. So cancel the 2's and you get G sine theta times L. And so V is, don't forget to square root. Okay, so if you use energy first, the first two parts were, you could grade them two ways. You can do them with the energy first and then the use kinematics to find the acceleration. If we do energy, we have potential energy, so The height, notice, is the sine component. So mg sine theta L is since the hoop is hollow, all of the mass is out at distance r. R times omega is v, so you have two halves of mv squared is going to be mg sine theta L. Kanka, v is square root of g sine theta L. And then you can work your way backwards through v squared equals v naught squared plus 2ad to figure out that the acceleration is half of g sine theta. Okay, so after that, horizontal distance. Remember, horizontal distance only depends on the time that it takes. So we're going to need kinematics to find the time. Notice also that the velocity that you leave with is exactly a horizontal velocity. So v times t, d is v times t, and we know that v is the square root of g sine theta L. So let's just figure out the time. It follows a distance of capital H. We have done this several times. Stuff that in. D is going to be square root of g sine theta L times square root of 2h and g. Oh, the g's cancel. So you have a nice horizontal distance. All right. If you replace the hoop with a disc, what will happen? The disc, okay, so if you have a disc rather than a hoop, the I is less because more of the mass is concentrated closer to the center. So we're not dividing by as much to get V. And also A is greater. Notice that the time that it takes to fall is not different. Because that only depends on the velocity, the vertical stuff. And the vertical stuff starts at 0 velocity. But the horizontal velocity is now greater. So it falls further. Okay, so point values. Out of the 15 point sections, the 2 sections are 8 points total, 5 and 3, unless you do 5 and then 3. So if you do the energy first, which is fine, notice if you're having trouble figuring out the acceleration because you don't know the torque, then you can do the energy equation first to get V, and then use kinematics to get A. And that's 8 points total. The next one is 4 points. 1 point for H is 1/2 GT squared. 1 point is for solving for T. 1 point is for D consistent with what you found for your velocity. And 1 point for combining it together. Last section is 3 points. 1 point for saying greater than, 2 points for a correct explanation.